Welcome everyone to the second workshop. I'm really excited to have you all here. And today I'm going to just do a recap on what is data structures, the importance of data structures, and then we're actually going to dive into trees today, and then we'll go through binary trees and how to traverse them, and then I'll also give more examples of tree data structures. Okay, cool. So just to recap, a data structure is a particular way of organizing data in a computer so that it can be used efficiently, right? In the previous workshop, I shared this exact same image over here, and as you can see, last week we covered the primitive data structure and we went into the linear branch there, covering arrays, linked lists, stacks, and queues. And like I mentioned today, it's all about trees. So, firstly, what is a tree? A tree is a non-linear hierarchical data structure that consists of nodes connected by edges. When operations are performed in a linear structure, the complexity arises as the data size increases. On the other hand, the tree data structure provides much quicker access to data which is non-linear. The data structure is called a tree because it resembles a tree. It starts with a root node and branches off with its descendants. So as you can see in the image on the right, that's an example of a tree. Um, and you'll notice that it looks like it is actually an upside down tree, but trust me, that's how it usually works. So I'll go through some like real life examples of trees that I'm pretty sure everyone knows. So first of all, something like a family tree, right? Where you can see in the image, we have your grandparents, and branching from those, it could be your mother, and your uncles and aunts, and obviously your mother and father would have you and your siblings. So this you can see is an example of a tree data structure. The next example is one of a organizational structure. See, noting that the root node over here in this example is the CEO, and then we have below that the CFO, CTO, and CMO, and below those would have um, other employees that fall under those um, managers. The next example, for all the web devs out there, you can see that the DOM is actually another example of a tree, knowing that each HTML file would start off with your HTML tag, and then we would have your head, body, and all of the tags that would follow in them. Okay. The next example over here would be like a file system. So we would have your root directory, and you can see all of the other directories that follow those, follows underneath root. So before I get started with more on more about trees, there are some terminology that I would need to just explain so that everything that I will cover later would make more sense. So firstly, let's start off with the root node. So in a tree data structure, the first node is called the root node. So every tree must have a root node. So we can say that the root node is the origin of the tree data structure. In any tree, there can only be one root node. We can never have multiple root nodes. So here in our example, you can see A is the root node, remembering that the first node in a tree data structure would be the root node. Okay. Next, we have edge and the connecting link. It's the connecting link between two nodes. Um, Note that in a tree with n number of nodes, there will be a maximum of n minus 1 number of edges. So you can see in our example over here, our edges are connecting two nodes. Next, we have parent node, and it's the node which is a predecessor of any node would be called the parent node. In simple words, the node which has a branch from it to any other node is called the parent node. So the parent node can also be defined as the node from which there's child or children nodes. So in this example here, you can see that A, B, C, E, and G are all parent nodes since they have children following that. And that actually takes us to the next term, would be child. So the node which is the descendant of any node is called the child node. So like I mentioned, if it has a parent node, um, that node itself would be, the child. So in this example, we can see that B and C are children of A, G and H are children of C, and K is the child of G. Next, there's siblings. So nodes which belong to the same parent are called sibling nodes. In simple words, the nodes from which they have, the same parent is called, sibling nodes. So here in this example, B and C are siblings, D, E, and F are siblings, and I and J are siblings. Notice also G and H is also sibling nodes. Next, there's the leaf. So the node which does not have a child is called a leaf node. So the only thing you when remembering what a leaf node is that if a node does not have a child, that node itself would be called the leaf node. It's also called a external node. So external node, um, whenever a node does not have a child, it can also be considered a external node or a terminal node. So in this example, you can see that D, F, H, I, J, and K are all leaf nodes. Next, there's internal nodes. So the nodes which has at least one child is also called a internal node. In a tree-dot structure, nodes other than leaves would be then considered a leaf node, an internal node. Next, we have degree, and it's the total number of children of a node is called as a degree of that node. So in this example, we can see that the degree of A would be 2 since it has two children. The degree of B would be 3, and the degree of F in this example would be 0 since it does not have a child. Next, we have levels. So in a tree-dot structure, the root node is said to be at level 0, and the children of the root are at level 1, and we can see their children would be then level 2, and it will go on until we reach the end. Next, we have height, and it's the total number of edges from leaf nodes to a particular node in the longest path is called the height of that node. So in a tree, height of the root is said to be the height of the tree. In a tree, height of all nodes starts at 0. Next, we have depth, and the number of edges from root nodes to a particular node is called as depth of that node. In a tree, the total number of edges from a root node to a leaf node in the longest path is said to be the depth of that tree. Um, in simple words, the highest depth of any leaf node in a tree is said to be the depth of that tree. So you can see over here, um, instead of the numbers that we see here for height, it's pretty much reversed over here. Next, we have path, which is the sequence of nodes and edges from one node to another. A length of a path is the total number of nodes in that path. In this example, the path A, B, E, J has length 4. Next, we have subtree, and in a tree data structure, every child from a node forms a tree recursively. Every child node will form a subtree on its parent node. So you can see over here in this example that how subtrees are formed from the parent node. Okay, so let's get started with binary trees. So a binary tree is a tree data structure in which each node has at most 2 children, which can be referred to as the left child and the right child. So here in this example, you can see what a binary tree would consist of. So we would have the data item that we have there, and then we would have the address of the left child and the address of the right child. So there's also different forms of a binary tree. So the first one we're going to have a look at is a full binary tree, which is a special binary tree which every parent node or internal node has either 2 children or no children. The next one we're going to have a look at is the complete binary tree. And a complete binary tree is just like a full binary tree, but with 2 major differences. So every level must be completely filled. All leaf elements must lean towards the left, and the last leaf node might not have a right sibling, i.e., a complete binary tree doesn't have to be a full binary tree. Lastly, we have our perfect binary tree, and it is the type of binary tree in which every internal node has exactly 2 nodes, and all the leaf nodes are at the same level. So next, I'm going to take you through some representations of a binary tree. So notice that in this examples we have representations for JavaScript, Java, and Python, and this would be just the base of it. But obviously, once you need to implement some operations, the class would increase to account for those different operations. Okay. Next, I'm going to go through the pre-order traversal, in-order traversal, and post-order traversal. So it is key that you understand these traversals so that we can adapt them to other problems. If we are very flexible with traversing a binary structure, it becomes easier to solve problems recursively or iteratively with a stack. So notice that, just quick note that these are just fundamental traversals that I'm going to go through, but they are more out there. So firstly, let's go through the pre-order traversal. And we're going to basically use the tree on the right. We're going to traverse through that using the algorithm that I have there on the screen. So the first thing we can see there is visiting the node, moving to the left subtree, and moving to the right subtree. So the way this works is that, and you can see that in brackets over there, I have N, L, and R, which is basically represents the steps in the algorithm. So how this would work is you can place you can think of each node having um, this policy of going through each one of those steps. And by going through each one of those steps, it will result in the output that you can see on the screen. So let's start at 10, right? So we know that, like I mentioned, all of these nodes would basically have N, L, and R, which would be go visit the node, go to the left, and then go to the right. So that goes for 10, 11, 7, all of those numbers that you see on the screen. So let's start at 10. So we go through 10. So 10's first policy or first rule would be to visit that node, and that's what we actually get in the output. You can see we first have 10, and then the next step for 10 would be moving to the left subtree, right? So now we go from 10 to 7, right? So now we have 7 over here, and now we note that 7 still has N, L, and R, right? So the first thing we need to do at 7 is visit the node, right? So now you can see in our output that that's why we have 7 over there. The next step would be to move to the left. So we go down to 6. So 6 would still have rule all of its instructions in there. So the first thing being visit the node. So you can see in our output we have 6, and then we moved to the left, right, which would go to 1. So now we're at 1, and we still have all of its rules. So next we would visit that node, and you can see it in the output, and next we would go left. But now in this case we can't go left, so we need to follow its next rule, which means going to the right. So since there isn't a right, we now move back to 6, right? So we already visit the node at 6, so and we moved to the left. So the last thing to do at 6 would be to move to the right. But you can see in our example that there isn't a right subtree. So what we do, we move back up to 7. So now that we're back at 7, we already went through the node, we already went to the left subtree. So the only thing left to do at 7 would be to move to the right. And then we at 8, and then obviously we're going to follow that algorithm again by going to visit the node, and you can see that in our output. And then we go to the left. But since 8 does not have a left subtree, it will then go on to the right. And you can see it's going to follow the same pattern of visiting the node, moving to the left, moving to the right, until you can see you'll get the output that you see on the screen over there. Next, we'll go through the in order traversal, and you can see the only thing that really changes through each of those traversals would be, the different policies that we have to, go through. So instead, in order, you can see that um, where we visit the node would be in the middle. So you can also take note of the prefix of, pre-order or in order, right? Or the lastly, it would be the post order. So that would just be an indication of where exactly we would visit the node. So in this example, let's try to go through some of the traversal for this trees, right? So we already know that, like in the previous one, where all of them had N, R, N, L, and R. each node in this tree would have L, N, and R. So we will start at 10 and then go through all of those steps. So going from 10, we would then need to go left. So now we're at 7. Next, we then have to go left again, since that is the first step. And now we're at 6. Since we're at 6, now we have to go through its first step, and that takes us now to 1. And 1 would try to go to the left, but there isn't a left subtree. So what it has to do now is actually visit the node. And you can see that reflecting in our output. Next, it will try to move to the right subtree, which it does not have. So what we have to do next is then backtrack and go back to 6, right? So now that we're at 6, we already went through the left. So now we can go visit the node, and you can see that in the output. And next we'll go to the right, and there isn't a right. So what we do, we move back now to 7. Now that we're at 7, we have to, we already went to the left, so now we have to visit a node and just output that, and then we go to the right. So now that we're at 8, it still has all of its rules there, so we need to move to the left, which it can't. Then we have to visit the node itself and then move to the right, which takes us to 9. And you can see that we have we will basically go through each of those rules for all of the nodes. A cool thing to note about this is that the output of this particular tree, we're actually getting all the numbers in order, and that's only possible due to the type of tree that or the type of binary tree that we actually have here. Um, this tree that you see is actually an example of a binary search tree, which I'll explain after I go through this traversals. Next, we have the post order traversal. So notice how the policy changed over here. So we move left, then to the right, then we visit the node. And let's see how how we will actually traverse this one. So we start at 10, we move to the left, right? So now that we're at 7, it still has all of its rules, so we need to move left again to 6. Then 6 still has all of its rules. We go then to the left again at 2, 1. So now that we're at 1, the next step for us to do is move to the left. It can't, so we need to move to the right. Still can't. Now we actually visit the node itself, and that's where we get our first output over there for 1. Next, we have to backtrack again to 6. So we already moved to the left. Now we're going to try to move to the right, which it can't. So what we do is then visit the node. And now we have 6 in our output. So once we've done the node visit, we go back to 7, which still has the right visit and the right, moving to the right and visiting the node. So now that we're at 7, we have to move to the right, and then 8 needs to then move to the left. It can't, so it will then try to move to the right, which takes us to 9. And then 9 will go through the first 2 steps. It sees that it can't go through, it can't find a left node, a left subtree, or a right subtree, so it will then visit its node. So you can see how that reflects in our output. Next, we have to then backtrack and go to 8, which would then need to, we would need to then visit its node, and then we go back to 7, which we completed the left and right visits. So now it needs to go to, it needs to visit the node itself. So that's why we have 7 over there. And you can see how, we will eventually go back to 10 and then moving to the right to get, all of the, or the left, the rest of the output that you see on the screen. So, like I mentioned, the tree that we actually used in those traversal is a form of a binary tree called a binary search tree, which, like I mentioned, is a subtype of binary tree that organizes is in such a way that it allows for faster searching, lookup, and addition or removal of data. So the representation of nodes in a binary search tree is defined by three fields, like the left, the daughter, the left, and the right child. So the binary search tree is governed by the following factors, right? So every node on the left side must have a value less than the value of its parent node. So we can see in this example that um, 7 is less than its parent node 10. And if we go down and check for others, like 6 is less than 7, 1 is less than 6, all of those other numbers would follow that. Next would be the values on the right side. So the right child must have a value higher than the parent. So you can see that uh, for 10, the right child would be 11, which is more than 10. 22 would be more than its parent, which is 20. And 9 would be more than its parent, which is 8. Okay, sorry about that. An arrangement like this reduces the search time to half of a linear search as found in an array in comparison to other abstract data types. Binary search trees in data structures are widely applicable for searching and sorting, despite the fact that both binary trees and binary search trees are primarily trees in data structures. Um, but just try not to get confused by the two, where binary trees are mainly just trees that has two or at most two children. With binary search trees, there is an order of um, the values. Next, we have the Adelson-Valsky-Landis tree, or just AVL tree. And as you can see, the data structure is named after the creators of the tree, and the tree it's a self balance. The tree has self balancing characteristics, which is unique. The heights of two subtrees from its root nodes are limited to 2. So the child nodes are rebalanced when the height difference exceeds 1. So for AVL trees, the heights are balanced or rebalanced through single or double rotations. So the balancing factor is the difference in height between the left and the right subtrees, and its values are, as you can see in this diagram, -1, 0, and 1. The next type we're going through is red black trees. This type is similar to the AVL trees because red black trees are also height balanced. What differentiates them is that they can be balanced in less than 3 rotations. So they have an extra bit that defines whether a node is red or black, and these colors are mainly used to make sure that the tree remains balanced during insertions and deletions. So during changes, the red black color coding is also repainted, but at almost no extra cost of memory. Next, we have splay trees, and the splay tree is a subtree or subtype of the binary search tree and has a unique feature of performing rotational operations to adjust the most recent node. By performing a rotation, the most recent access node is arranged as the root node. Although it is a balanced tree, it is not of the height balance um, variety. So as tree rotations are performed in a specific manner, the act of splaying occurs after the initial binary tree search. The tree is rotated to balance itself after each operation, and the search node is arranged at the top as the root node. Next, we have trees. So trees are a combination of trees and heaps in data structures. In a binary search tree, the values of the left child must be less than, like I mentioned, it must be less than the value of the um, root node, while the right must be greater. So the root node in a heap data structure has lower value, and its children nodes, both left and right, have higher value. So as a result, a tree has a value in the form of a key and a priority. The nodes with the highest priority are inserted first into a binary search tree so that the priority numbers are random independent random numbers. They keep a dynamic set of ordered keys and support binary searches within them. Lastly, we have B trees. So B tree is a self-balancing type of tree in data structures that sorts data in logarithmic time to allow for search, sequential access, deletion, and insertions. A B tree, unlike a binary tree, allows its nodes to have more than two children. They can read and write larger blocks of data in databases and in file systems. So in data structures, a B tree is used for larger storage systems such as disks. Um, all, all of the leaves contain no information and appears on the same level. A B3 internal nodes can have a range of child nodes with varying sizes, as shown in the example over here. And yeah, that pretty much brings it um, to all the other types of trees. Um, but and in conclusion, yeah, they are they are the trees in data structures that um, these are the trees that in data structures that programmers use to design the flow of data. So understanding their distinct characteristics and applications is important to your journey to become, or to be a better programmer. Another way to improve your skills would be to, work on projects that require knowledge of trees in data structures and any other, abstract data types.